Okay, good afternoon, everyone. My name is Sunyang Fu. I'm from UTHealth Houston. And now I'd like to help to kick off our next session, which will be Student Research Showcase, to feature our rising stars and showcase their innovative projects. We are showcasing our 6 finalists out of 20 submissions to select 3 winners. Before we get started, I'd like to express my gratitude to 6 amazing judges. So we have 3 reviewer judges, including Dr. Kyung-Hwan Chung from Baylor College of Medicine, Dr. Jeff Wang from UTMB, and Dr. Minji Kwok from UTHealth. And we will have 3 presentation judges, including Dr. Martin Rodman from UT Austin, Dr. Joseph Butner from MD Anderson, and Dr. Mohammad Wajid from UTHealth. Now, please welcome and join me to welcome our first presenter, Zehan Li from UTHealth.
Hi everyone, my name is Leo, and I'm a PhD student at UTHealth Houston and a member of Team AI. And my work focuses on AI for mental health. And I have 4 minutes to show you how I used a reasoning large language model to generate explainable suicide phenotypes using psychiatric notes. And buckle up, this is going to be fast. So first question, what is suicide phenotyping and why it is important? So imagine this scenario where David, a 16-year-old, came into the clinic presenting a suicidal ideation, past suicidal attempt in the last year, and now he complains about blaming his uncle for taking his own life, and now he regularly cut himself given whenever he's stressed out. And these are crucial clinical information in a hospital. But these information are only available in the clinical notes, and these notes are notoriously implicit, and these information are complex, written in narrative format. So the traditional language NLP are having troubles and struggling with these tasks. And we have very good reasons to hypothesize these new latest reasoning large language model will be a great fit for these, for processing these type of complex information. So we got examples from GPT-O series, DeepSeek, the Queen models, and these reasoning models essentially generating more tokens while it's in the background, emulating the human cognition, so improving on complex problem-solving situations. And these models were trained for longer, prompting longer before giving out a outcome. And another benefit of these models, they are equipped with structured output formatting. So in this study, we asked 3 questions. First being, how well do the in-context learned O-series model perform on multi-label suicide classification task compared to the previously fine-tuned GPT 3.5 Turbo? And second is, how interpretable, how useful are the generated clinical justifications? And thirdly, what are the clinical implications? So our method, we created 500 notes for gold standard data sets. And for each notes, we assigned 4 possible suicide phenotype labels, including suicide ideation, suicide attempt, exposure to suicide, and non-suicidal self-injury. So these 4 models, we were asking them to do 3 tasks. First being multi-label classification, explanation of each classification, and then evidence extraction. So as a result, we see the model perform very well on these multi-label classification tasks, and it is noteworthy to see that O3 Mini as a out-of-box large language model perform equally and even slightly outperforming the fine-tuned GPT 3.5 Turbo. And it is worth noting, it is a big deal for us. I mean, literally a deal in terms of the price to deploying the model. it is far more cheaper to deploy a O3 mini reasoning model than fine-tuning a large full model. And on the label side as well, even with this skewed label set distribution, we have very good output performance on each of these labels, especially on the label samples are few. For example, the exposure to suicide only have 22 cases. However, our F1 scores on these label set is about 90. So lastly, our psychiatry team of 5 are actively evaluating the quality of these clinical justifications as well, the evidence extracted from the original notes. So with the preliminary data, we see among the psychiatrists, we have a high agreement of high classification performance, and it is being judged as actionable and insightful. So you can read more of my paper, more on the error analysis. We systematically examine the pros and cons for each model for the reasoning task. And lastly, thank you for my PI, Dr. Liu and Dr. Huang, and appreciate it. Thank you.
Okay, our next presenter is Georgia Letchford from UTMB.
Awesome. Hi, my name is Georgia Letchford. I'm a UTMB medical student, and today I'll be presenting, let's see if it's up there, my project, which is a scope review patient perceptions of artificial intelligence in the screening, diagnosis, and treatment of various cancers. So to begin, our question here today is, in what scope do patients prefer AI in medical decision-making for cancer care, and what are their associated perceptions of such use? So to begin, some background. As we know, AI is gaining traction in the medical field. That's why we're all here today. And AI really has the power to tackle patient-reported suboptimal cancer care described across studies. This suboptimal cancer care is largely due to lack of appointments and dissatisfaction with counseling. But with AI use, there's definitely ethical concerns we need to consider, and this is especially true for cancer care, which is a complex and life-altering diagnosis. So we want to understand, how do patients perceive the use of AI in their cancer care? So to begin our methods, we did a scope review on Google Scholar, and after exclusion and exclusion criteria, we had 17 articles that we have reviewed so far. Our results are broken up based on different stages of cancer care. So to begin, in screening and diagnosis, the main findings we found so far is the majority of patients believe AI is to be used as an adjunct to physicians, and interestingly, patients are more willing to believe the opinions of physicians over AI, which is what this figure shows. This figure also emphasizes the idea that patients want physicians to be using AI as adjunct tools, and interestingly, in this study, 50% of respondents found that they believe physicians should be accountable for AI errors, which is something we should take into account when we use AI in cancer care. So in terms of prognosis, one study found that cancer survivors had a positive opinion towards use of AI, especially when it gives them more information, gives them tools to see patients like themselves, and which reported feelings of less isolation. There was also a strong preference for an oncologist to be present due to the sensitive nature of these conversations, and they wanted help understanding these statistics that they were being given. In terms of treatment, the majority of cancer patients found in one study reported distrust in AIs when creating a treatment plan, and similar to what we've seen in the past 2 slides, they preferred follow-ups with human doctors. In terms of some demographics differences noted, there were differences in gender as well as education, but also there were differences based on medical history. Those in one study who had a history of melanoma were more supportive of AI in screening than those without a history of melanoma. So all of this to say is patients perceive that AI can help tackle these suboptimal cancer care issues that they have, whether it be reduction in wait times, increased survival rates, it can also maybe reduce healthcare costs, or increase diagnostic speed. But with AI, they also have concerns, whether that's privacy, biases in algorithms, or hindrance of the patient-provider relationship. Some limitations to our study is that these studies only focused on breast, skin, and prostate cancer, and most of the patient populations in these studies were predominantly white with a higher income and education level than the general population. So in conclusion, there's 3 main points we took away from the readings we've done so far. One is that patient communication is key. We need to be transparent about the use of AI. Second is that patients doesn't want AI to replace physicians. They'd rather see it as adjunct use. And lastly, the patient-physician relationship is what is key to all of these things. They want an enhanced patient-physician relationship, and if AI can help provide that, they're all for AI. So future directions we can take this study is we hope to expand the demographics and look into other various cancers. But for now, these are our references, and you can email us with any questions you have. Thank you so much for your time.
Okay, next speaker is Roscoe Stoinch from UTHealth.
Let me go back. All right, good afternoon. My name is Roscoe, and today I'll be discussing our research on ogluconacylation and dysregulation in cancer. So first, very briefly, what is ogluconacylation? Well, it's a very unique post-translational modification. Basically, key features of this modification that make it unique are that it happens on thousands of different proteins, which are involved in many downstream pathways, many important regulatory pathways. It's very dynamic and rapidly cycling, and it's regulatory simplicity. So it's only controlled by 2 enzymes, single writer OGT and single eraser OGA. So what does this mean? The dysregulation of this modification disrupts critical downstream functions, leading to many cancers' onset and progression. And some issues in ogluconacylation research are that its speed and ubiquity of cycling make it very difficult to measure, which makes data on it very limited, and difficulty with using OGT or OGA as therapeutic targets because of the high off-target effects. But 3 factors open up an opportunity to study ogluconacylation dysregulation in cancer. So first, the regulatory simplicity, so not a lot of moving parts. 2, there's publicly available large gene expression data sets. And 3, many of these downstream ogluconacylated proteins are known and have been well cataloged. So the key questions are, could we, 1, use this regulatory simplicity and large-scale expression data to infer this dysregulation? And 2, could we include then these cataloged downstream proteins to identify cancer and progression related downstream pathways? So the first question, we gathered and used the largest TCGA gene expression data sets, and we built a kernel density estimation based methodology to infer regulation or dysregulation based off of OGT and OGA expression. And the methodology worked, and we validated it on the cancers that we explored. For question 2, we needed to build these downstream functional gene networks, which we did from harmonized data of these downstream genes. We then developed a methodology for determining importance of these downstream networks in differentiating between any 2 cohorts of patient expressions. So this allowed us to select, you're able to select a cancer and a cohort to compare, and then you're able to derive the most important subnetworks for differentiating those 2 cohorts of patients. So then you can explore if these networks are biologically relevant to that specific cancer and the survival of patients. And both of these are done, are cancer specific, and they're both done on outside data sources, so more robust. And our results indicated that our methodology identified critical subnetworks of these ogluconacylated genes related to specific cancer and survival rates for most of the evaluated top networks for all of the cancers looked at. We're still waiting on some results. But this research helps us move beyond simple OGA, OGT, and helps us identify potentially safer targets It improves our understanding of this process in cancer, highlights risks and protective pathways, supports biomarker discovery, and is adaptable framework, so you can use it for different phenotype or different post-translational modifications. So to close, our work addresses a knowledge gap that while this process has been linked to tumor progression, its system-level role remains poorly understood, and there's no established framework to analyze dysregulation or its downstream consequences. And to address this, we developed this scalable computational framework to do this. So these are the people I'd like to thank in my lab. And if anyone has any more questions, you can email me or go see our poster upstairs. So thank you.
Okay, our next speaker is Awas Nai from UT Houston. So welcome.
Hi everyone, I am Awas Naim from UT Houston, and today I will be presenting Path Agent, in which we try to mimic the diagnostic workflow a human pathologist will follow while they are trying to answer the open-ended pathology visual question answering. So before we go further, I would just like to explain that what is visual question answering. So if you have an image and if you have a question and you pass it to a vision language model, you basically get an answer. If the answer can be yes or no, it's basically a close-ended question. But if the answer basically, if the answer can be any text, then it's basically a close-ended, it's an open-ended question. And such questions, usually start with why, when, and where. And this requires a quite comprehensible, deeper learning models. But when we go from normal images to pathology images, now most of you won't be able to understand this question if you're not a pathologist. Even I don't understand it. But the thing is, there are already some visual language models which are already trained, or foundation models. And if we get an answer out of them, which can be either a yes or no, such vision language models are actually able to give us these answers correctly around 90 to 92% of the time. But if we just convert these to open-ended questions, then that accuracy or the same models actually falls below like around 38% to 60%. And the major issue is that the pathology images have like some intricate structures, and there are some difference in cell composition when you're looking at the images which are either cancerous or non-cancerous. So this basically presents another workflow in which we have tried to devise an agentic workflow in which we are not fine-tuning anything. We are just using off-the-shelf models and try to incorporate different agents. So firstly, how a pathologist collects their knowledge base. Obviously, all of you know they need to go to the med school and graduate. And once they graduate, if you pass a question to them along with an image, they will go to their memory, brain memory, and maybe, like in today's domain, they will go through the books and try to answer the question. So we try to mimic the same thing. We get like 1 million image caption pairs, which is quilt 1 million data. And then we try to fine-tune a contrastive learning model which basically aligns each image to its caption and disaligns to all of the captions. Now, when we do it with the 1 million image caption pairs, we basically get a model in which when you pass an image, it will give you the relevant text. So this was our training part. And how the inference was working, we just pass in an image, and then we also used a chief, which is also like a foundation model, which was trained on a weakly supervised learning using the tiles of the images or patches of the images, and it was also unsupervisedly trained on whole of the WSI slide. And it was able to give us the anatomical side, where the image is coming from. Is it from bone? Is it from neck? Is it from somewhere else? So we got our subpathology. We got that retriever. We trained 18 retrievers, and then we basically got the knowledge base in the form of captions. So that's how we mimic the knowledge base of a pathologist. The next thing a pathologist normally does, they basically try to scale the images to 20x, 40x, 100x, 200x, and try to gain different information out of them. So what we did, we basically took an image, we basically divided it into tiles, which was around 224 pixels, close to 224 pixels, and then we again used an off-the-shelf tool, histocartography, which just gives you the number of nuclei which are present in each image, as well as in each patch. And then we dynamically selected the patches which had the most number of nuclei. The other thing which we did, chief. So chief is a model which basically divides the image into So we basically divide the image into different patches, and then it basically gives you the attention score of each patch related to the image. And we selected top 25 patches, and then we selected all the common patches, and that basically gave us like 3 to 6 patches. So the last thing a pathologist would do once they have all of these scaled images, they will try to consolidate all this information into one. They will go back and through, and then they will go through their brain, books, and try to form a final diagnosis. So what we did is, we took an image, and there was an ROI agent. So we took an image, we constructed a region of interest in that image, and so this ROI agent was basically LavaMed. This is again a vision language model. We also plan to use QuenVL, but for now we use LavaMed. And we just asked simply that if this patch is useful to answer the query, you need to give us the description of this patch. And then we had another patch agent in which we didn't pass the whole image, we just passed the patch and the knowledge base which we collected in the first step. And then we made them go through the N rounds. And once they went through it, there was another critique agent in which we passed all of the information, the image, the patch, all the knowledge base, and it basically critiqued and refined all of the information which we had. So at the end, we basically did this for each patch, and at the end we basically had summaries of each patch, which we extracted in the first step. So the last step was we basically got the captions, we basically got the summaries, and we passed it to GPT-4 or another VLM to get the final responses. So this is the whole architecture, how it looks like for 2 patches. Obviously, we are not extracting 2 patches. We can extract 5, 6. And these are the results, which actually show you that our algorithm actually improved like around 100% on top of it. So my time's out, but if you have any questions, please reach out to us. Thank you so much.
Okay, our last speaker is Charlie Yi from UT Austin.
Thank you for having me today. I'm Charlie, and I'm a PhD student in the Department of Biomedical Engineering at UT Austin. Imagine that your child has undergone 2 open heart surgeries before their 2nd birthday. You're told that they can finally go home, but instead of feeling relief, you're now left with questions. What happens next? So this map shows the lifelong journey of patients with single ventricle congenital heart disease. After 2 major surgeries, many children are discharged, but that's just the beginning. As they grow, they face critical transitions such as starting school, losing insurance, entering adult care, and often without the support they need. Much of this journey unfolds beyond the current healthcare system. Even with the surgical advances, families still face gaps, especially during transitions that I just stated. What's missing is not the treatment itself, but a way to understand what matters after surgery across families. Manually analyzing one-to-one interview transcripts can partially reveal these gaps, but it doesn't scale. It took several months of expert effort to analyze transcripts by hand, and that's where our approach comes in. Using AI agents with diverse identities to uncover population-level patterns in a way that is fast and scalable. Our multi-agent AI framework mirrors how real care teams interpret stories through multiple perspectives. We assign roles to large language model agents, such as psychologist, surgeon, or a qualitative researcher, and have them analyze the interview transcripts. These agents generate codes, which are the building blocks of qualitative research, and these codes are then synthesized into overarching themes, which represents gaps in care. This speeds up the whole analysis process into a couple of hours, whereas it was several months before through manual analysis. And with this method, we can uncover insights that a single LLM agent might miss. Our results show that identity-based agents outperformed a single agent baseline in both code alignment and theme coherence. Thematic similarity scores increased when combining perspectives, like when a surgeon and a psychologist work together. More importantly, they uncovered themes that mattered to families, such as surgical trauma, which were often overlooked in manual analysis. These are the insights we can build interventions around. So in summary, today, our framework already automates the thematic analysis process using identity-driven agents. The next step is making that process smarter. We're introducing a feedback agent that critiques the themes from generation agents, asking, what did we miss from the original transcript? Or what truly resonates with families? Human experts and reviewers will guide the reviewer agent through reinforcement learning to make it more aligned, trustworthy, and useful. Thank you for listening.
Thank you very much. I haven't done math for a while. The first and second place only has 0.5 points difference out of 50 scores, and the third and fourth and fifth only have 0.25 difference. So we're gonna give the fourth and fifth honorable mentions because they are just so close. So please join me to congratulate the third place, Charlie E., UT Austin. And the second place, Awas Nai from UT Austin. All right, first place, Leo Lee, UT Austin. I'm sorry, UT House.
Yes.